There are ways that we can identify the position of atoms within a solid. And one of those ways is by using X-ray diffraction. You can actually send X-rays through the crystal structure of an atom, and we end up with a diffraction pattern that we can detect using an X-ray detector. If we very slowly let a solid form from the liquid state, this allows the atoms to have the greatest attractive forces, and it generally results in a crystalline solid. And there's actually contests throughout the country in order to grow very large crystals. So that arrangement, when those particles form into that crystalline solid, is what we refer to as a crystal lattice. And if we look at the very smallest part that has that repeating pattern, this is what we call a unit cell. So the arrangement of those atoms in the smallest unit is our unit cell. Unit cells are what get repeated over and over to give that overall large crystal structure of a solid. So if you've ever seen sodium chloride under a microscope, it gives you kind of cubic crystals, and that's because of its unit cell. And so it is a three-dimensional representation of the atoms. And each particle within that unit cell is called a lattice point. So the example that's given, that's shown here, we have the center of each atom in the corner of our unit cell, and this is what's referred to as a simple cubic. So 1/8 of each atom is represented in the corner of our unit cell. There are many different types of unit cells. The one that we're going to focus on is the cubic unit cell, in which all of the sides are equal in length and all of our angles are 90 degrees. If you remember back to when we were looking up the elemental forms of different elements for enthalpy, you might remember that we saw some of these other types of unit cells, like rhombic, like monoclinic. These are referred to the unit cells and the arrangement of the atoms in their elemental form. Unit cells can have different characteristics. One of those characteristics is the number of particles that each particle in that unit cell is touching. And so if we're talking about ionic compounds, this is the number of oppositely charged ions that it has contact with. The higher that coordination number is, the more efficiently the particles are packed together. And so this is what we call the packing efficiency. And packing efficiency is the percent of the volume in that unit cell that's occupied by particles as opposed to just empty space. So the higher that packing efficiency, the higher that coordination number, that means that there is stronger attractive forces that are able to hold that crystal structure together. When we're looking at cubic unit cells, we're thinking about our molecules and how they exist within a cube. And so cubes have equal lengths on each of their sides, and all of our angles are 90 degrees. If that particle exists at the corner of the cube, that means that 1/8 of that atom is occupying inside that unit cell. Now, if we have the case where it's on the face of the cube, so on one side, that means that half of that atom is on the inside of the cube and half would be on the outside. But because we talk about unit cells looking at the inside of that cube, only half of the atom is on each of the faces. If a particle is on the edge, so if it exists along the edge of the cube, then a quarter of the particle is on the inside of that cube. So if we look at a simple cubic has 8 atoms, each at a corner of the cube. So that means that because it's on the corner, an eighth of each atom is on the inside of the cube, and there's 8 total. So if we multiply 1/8 of each atom by 8 atoms that are in the cube, we end up with 1 complete atom in our simple cubic unit. Now, if we think about our coordination number, as we look at the atom, it is able to touch 6 other atoms. So our simple cubic has a coordination number of 6, and the number of atoms within that unit cell is 1. If we look at bodied center cubic unit cell, now the bodied centered means that we have 1 atom on the inside of the cube, and then there are 8 other partial atoms in the corner. And so each of the ones on the corner has 1/8 of the atom inside the cube, and there's 8 of them, and then the 1 atom that sits at the center. So inside our cubic cell, our cubic unit cell, there are 2 full atoms. If we look at the coordination number, that 1 atom sitting in the center of the unit is touching 8 other atoms that sit at the corner. And so our coordination number is 8 for a body-centered cubic unit cell. So these are different examples of that simple cubic. The last example of our simple cubic is the face-centered cubic. So for the face-centered, we have half an atom on each of the 6 faces of the cube, and then a partial atom at each of the corners. So we have 1/8 at each of the corners of our cube times 8 atoms. And then that face-centered, only half of the atom sits inside the cube, and there's 6 faces. So this gives us a total number of atoms inside our unit cell of 4. And if we look at our coordination number, now each of those atoms is touching 12 other atoms. So here's a practice for you. Try to decide which of the following is the closest packed for our cubic unit cell. Which one is closest packed? Well, our closest packed is going to be the one that has the most atoms inside the cell. And so this is going to be our face-centered cubic unit. There are lots of different types of crystalline solids. So we have molecular solids made out of molecules, so these are covalently bonded. These would be things like ice. They tend to have lower melting points than things that are like ionic solids. Ionic solids, remember, made out of metal and nonmetal with an ionic bond. They have much higher melting points. So these are things like table salt or sugar. We can also have atomic solids. So things that are made out of atoms. So these would be things like metallic solids, like gold. We can have things that are non-bonding solids, like xenon. So this would be the noble gas that when we cool it down, it doesn't bond, but it forms into a very low melting point solid. Or we can have network covalent, held together by covalent bonds. So these tend to be higher melting points, things like silicon dioxide. So that is quartz, which is a type of stone. Sodium chloride is an example of a simple cubic face-centered arrangement, where we have alternating pattern of the positive sodium ion with the negative chloride ion. And overall, our formula ends up to be 1 sodium and 1 chlorine. We also have other things like diamond. So diamond is when we have carbon that is arranged in a tetrahedral crystal structure. This has a very high melting point, about 3,800 degrees Celsius, because we need to add enough energy to overcome those covalent bonds. It is very rigid and hard. It is an electrical insulator, and it's chemically very non-reactive. So diamond is very non-reactive. Another type of crystal structure is graphite. And again, this is just carbon, but now we have hexagonal crystals as opposed to those tetrahedral crystals. Again, this has a very high melting point, but notice that our properties have changed. Now, because those crystal structures lay in flat sheets, so we have carbon in flat sheets, but then there's only intermolecular forces, so just dispersion forces holding the sheets together. And so that makes graphite very slippery because those sheets will slide over each other. And it's frequently used as lubricant. And it's also why graphite is used for pencils, because it's easy to shed those layers of carbon atoms. So the same element can have very different properties based on its crystal structure. As always, there's some suggested problems for you to try at the end of the chapter. Thank you.